So this is example number 1 for fatigue. Just as a review before we start the example, remember we need to have two diagrams. Okay, one is the this is the SN curve. This is the SN diagram. This is the fatigue diagram. And you plot this SA versus SM, and note that every value here under your endurance limit will be actually a value that corresponds here. Any value above the endurance limit is a value that corresponds here. Okay, so this is in general, and if this is yield, if it's ductile materials, it will be ultimate if it is brittle material. Okay, so the problem, you may want to stop the video and take a screenshot or write the problem. Basically, the problem is saying I'm going to use class 60 grade cast iron. Immediately, you know this is a brittle material. The problem states that. It is subject to tension and torsion, and is shown here in the figure how it is. You have two diameters. This is the smallest, this is a solid arm. So you have the solid diameter here at 2. The bigger diameter here, is D. So your big diameter is 2.25 inches. Your small diameter is 2 inches. Okay, and you have an R, a fillet radius, notch radius of 0.125. So this you get from the picture itself. It says that it takes 2 minutes for completion for a full cycle and it operates only 8 hours a day. And the ultimate tensile strength is 60 KSI. So the problem does give me my ultimate tensile. This is 60 KSI that's given in the problem itself. And I want to use an additional design factor of 1.5. Okay, so the problem gives me, says that tensile fluctuating load. Because it's tensile, well, I know in the problem that my load is actually, when we say 50,000 tensile, we mean that it's actually is fluctuating all in tension. Okay, that's your loading cycle, respect to time. And he also says your torsion is also in tensile. So the problem does give you this. Okay, so it's all in tension. This is your torque. This is your time. Then before we start the problem, we know it's giving me the maximum load in the problem because it says that it's fluctuating between a load here and a load there. But remember, the loads that we have to use are the loads that are multiply the design factor times the load that's given. Okay, so this is 1.5 times 50,000, and that will give me 75,000. Okay, and your torque will be your design factor times the torque that's given. That will be 27,000 inch-pound. Okay, so that's given in the problem, and this is pounds. So we know this information. Again, this is because this is 18,000 that's given in the problem, and this is 1.5. These are the values I will use. I have a value here of P max and a P minimum. Okay, T max and a T minimum. I don't have any bending in this problem, no axial, no any of these loads. So in your problem, P max is 75,000. P minimum is equal to 0. T max is equal to 27,000. T minimum is equal to 0. So before we start the problem, remember the first thing I want you to do in the problem is let's go and find what my alternate loads are. In this particular case, your alternate load will be my max minus my minimum divided by 2, and that would give you a load of 37,000. Okay, and also I want to find what is my mean. My mean is n max plus n minimum divided by 2. I use n as our general n, but remember this is actually p. Okay, and this is actually going to give me the same value. It's a coincidence that I get the same value. It doesn't necessarily has to be like that, or it's actually like that. Then for my torque uh, uh, is what we call MXX alternate. There will be T max minus T minimum divided by 2, and that gives you a value of 13,500 inch-pounds. MXX mean is the addition of these two loads divided by 2, and also just happens to be in this problem I get the same value. Again, doesn't necessarily have to be like that. Okay, so now that we have this, we have to build our state of stress. But before we build our state of stress, we need to find our load factors. Okay, so in our problem, big D over small d, and then I need to know R over small d. So this gives you 1.13. This gives you 0.063. So you are, this is almost on this line here, basically. And the value that I have here is 0.06, let's say somewhere right there. So this is just eyeball it more or less, and I come up here, and I might be a value just slightly higher here, but for the sake of this example, let's just take this equal to 1.8. It's close enough, okay? And then I need to have for torsion. Remember what I'm using for torsion. So in this problem, regardless of what you're doing, you need to always find these factors, regardless if it's ductile material or brittle material. Okay, and again, I am somewhere here, and 1.15. So I may be somewhere there. So I get that value, and I find my KTS is more or less just roughly, this is 1.2, 1.35, let's say. Okay, just eyeball it. I really don't need this value in the problem at all. I don't have this. So if you're going to solve it, you can just take this equal to 1 if you wanted to, but I really don't need it. I don't need it, okay? There is no moments. The moment in bending is actually equal to 0, okay? The other value that I'm going to need this value. The notch is 1.25. However, these plots are for steel and aluminum. You can see steel for aluminum. So those don't help me at all. This is the equation, standard equation I will be using. So I need to go to the next criteria that your book tells you. So it says that for cast irons, use 0.2. So that's the value that I'm actually going to use in this problem. So your KF A, okay, for this is, so let's say for axial, okay, is equal to 1 plus Q axial kTA minus 1. Okay, this gives you 1 plus 0.2. This was 1.8 minus 1. And then for torsion, I have KFS A. This is 1 plus QS KTS minus 1. 1 plus 0.2. And that gives you, we use the value of 1.35. 1.35 minus 1. Okay, so the next thing I need to know is the load factors. And if you go to the notes I gave you, you had several cases, okay? And the computer, your Matlab code actually calculates this for you very nicely. And the code, the option that we actually doing is option number 3, torsion and combined with axial. Okay, for this particular case, your KL for axial is 0.85. This is always 0.85. And KL at bending is 0.9, but we don't have bending at all. So KL at S or torsion is actually equal to 1. So we do this. Remember, this is only applied to alternate loads. Alternate stresses. We don't apply this to the mean stresses, okay, only to the alternate. Okay, so with this said and done, we are ready to build our state of stress in our problem. Note that your state of stress, alternate state of stress, will be given by, for alternate, remember we are using KFA. This is standard. And then this would be NXX alternate divided by area and divided by your load factor, A. We don't have no other additional loads. And we also have KFS, MXX alternate divided by your big Q, and this is divided by QL. And this is a symmetric matrix. So you have the following. Okay. So for this particular problem, your for a diameter of 2 inches, and I will let you show that, your area is equal to 3.414 inches squared. Your big Q is equal to 1.57 inches cubed. And applying these values that I got here, okay, once you apply those values, you get the following. So this actually equals to 1.16. This equals to 1.07. And you can see the value is smaller than the static value. This is fatigue. It's supposed to be smaller. It is completely reduced. Okay. So those are the values that I actually apply here. Use your KFA equal to 1.16 and your KFS equal to 1.070. I plug in these numbers inside here for each one of these values, and you find that your state of stress in for alternate is equal to, your alternate state of stress is equal to 16.29. This is all in KSI. This is 9.19, 9.1900. Okay, so now we need to build our mean. Okay, for the mean alternate, okay, for the mean, your state of stress is going to equal to, you also have your KFM, um, and then you have your NXXM divided by area. Here you don't have any load factor. The means do not have that. You have KFS, mean, MXX mean divided by Q, no load factors. For means, you don't apply those load factors. MXX mean divided by Q. Okay, and then here, what you have to know, the only thing that's different is that this, for the case for mean, we also use the same value for axial that we found in the previous problem. So this is actually 1.16, but this is we are working for brittle materials, and for brittle materials, that's what we do. So we are going to use the same values we got from the charts. This is applied to both. The only difference is I am not dividing this with my load factor. So if I did that, now my load factor, my mean state of stress will equal to 13.84, 0, 9.19, 0, 0, 0, 0, 0, 9.19. And this is all in KSI. Just remember, at the end of the day, what I really want is I want the principal stresses. I can run this on your Matlab code, and I really care for sigma 1. This is 20.43 KSI, because this is for brittle material. This is the one that we use. And sigma 1 in mean, that will actually equal to 18.43 KSI. Okay, these are the values I'm going to use. So for our analysis, we're going to set A equal to small for alternate, right? And that was equal to 2043, and big M is equal to 1M is equal to 1843. Okay, and this is all in KSI. These are the values I'm going to use for my analysis. Okay, so I have these values. The next thing I need is my S equivalent. This will be your von Mises, your Goodman stress, 1 minus S ultimate. And I have all these values here, 20.43, 1 minus 18.43 divided by 60, and that will give you a value of 29.49 KSI. Okay, so we know this value, So now what we need to do is we need to build the diagrams. Okay, the first plot is the first plot you want to do is you want to plot SM versus SA. Okay, so what I need to in order to plot this, I need my endurance limit, so I can plot this value, and I know that this value is 60 because that is my SUT. I don't have yield line. I have an ultimate line that would be 60 here as well, because this is actually, we are working with brittle materials. So in the case of brittle materials, this is what your stress level looks like. And then you're going to have a load line. Okay, your load line will be SA divided by SM. So that would be 20 divided by 18. 2043 divided by 1843, and you get a value of 1.11. Okay, so this is the value I need to complete this chart. So let's go ahead and calculate this. To find this, to find that, I need to know what my SE is. This is K infinite and multiply by SE prime. And you can see that for cast irons, if you look at your notes, your cast irons and your SUT is equal to 60, then in that case, your SE prime is going to equal to 24 KSI, and that actually happens at 10 to the 6. In the code that you're going to run in your Matlab code, this 6 is what it means to represent your G. Okay, so when your code is asking for G, it's asking for this actually superscript 6. For aluminum, it is 8, and so on and so forth. Okay, so this is what we really have. So now we need to find all these parameters. To do that, we can go ahead and calculate this. Do I have any additional loads here? My K1 is actually equal to KB. This is for shape. We don't have any criteria for shape, but let's take that equal to 1. Your temperature, you can go to your chart, equation 6.27. And if you apply that, you get a value of 0.028. This is temperature. This is size. And we don't never take this be greater than 1, so we reset this value to 1.0. The problem is saying that this is hot rolled. Okay, so this is the surface. How is the surface finish? In the case of surface finish, for this particular case, your K4 value will be A SUT to the B. You go to the tables, you find this is 4.4 SUT, and this is minus, B is minus 0.78. You evaluate this number, you get 0.76. You want 95% reliability. In the reliability, this is, I'm sorry, this is K4. And K5, this is your reliability correction for 95%. At 95%, you can go to the table, so use the Matlab code, and you find the value that you get is 0.86. So from these values, K infinite is nothing else than, I don't have no miscellaneous values here. It is the multiplication of K1, K2, K4, and K5 in this problem. And if you multiply all these loads, I get a value of 0.660952. So now your SE will be K infinite SC prime, and this has a value of 0.66. This has a value of 24. So you actually get a value, your final value of your endurance limit at 86 KSI. Okay, so now we have that, so we can go back and we can plug the value here and see where you add in a dot, and you will see that we're going to see that in the plot. I'm actually located here. The second thing I want to do is I want to build my SN diagram. Okay, so this is my load cycles. This is my alternate cycles. So I start at ultimate, and I want to see what my F is. I have a right here F times ultimate. Then you go here and you go to, and this is actually SE that we found is equal to 15.8 KSI. We found that value, and this particular value in this problem, you can actually find that using your Matlab code. Or using the criteria I gave you in the lecture notes. This is 0.9 for this example, times SUT, that was actually equal to 60. Okay, so now note something very interesting in the problem. Your Goodman stress was actually equal to 29.49. 29.49. This value is actually higher than this value. You can see that, right? So the value is here. If the value was over here, it would have been infinite life, but it's up here. So that means I am going to actually have this at some location over here. I'm going to have a finite life. And you can see that from this chart as well. I'm going to be located here that will actually represent finite life. So if you want to look how this plot actually look like in Matlab, your Matlab code actually plots this for you. And you can see that at the plots that you get this intersection. This is the intersection of this curve. This value right there, this is the load line, this is the actual load line, and this is the intersection of this. And just fact that you are anywhere here, anywhere inside this line, that means that you are actually, your problem is actually finite. Infinite will be if this load line would have been somewhere there. Now, you can also see the same behavior if I went and I showed you the ascent diagram that your Matlab code also gives you. And you run your Matlab code and you see your S equivalence up here. Okay. I have to fix this value. But then it comes over here. You can see I'm going to have a value there and I'm going to have a value here. Let me just show you how we run the Matlab code. To run the Matlab code, you're going to go and choose this fatigue theory main. That's your main file. From this file, just choose that. It's right here, and you hit you run it. So it says it's inches, and the design factor is 1.5. Nothing is given. 1.15 is the standard. Your load is 50,000. And this is the minimum is 0 because you're fluctuating, no bending. 18,000 and 0. The load case is number 3, and you can see that it automatically gives you load factors. Your circular, this is 2 inches. It was 1.8. Bending is 0, so I'm just giving you 1. I don't care. 1.35 was torsion. We are working cast iron. Ultimate was 60, and you can see that it actually calculates these values for you at 0.2. We are working for brittle materials, number 2, and this was 24. No shape correction factors. Temperature was 250, and you can see that I get this value, but it's reset to 1. The value of F is equal to 0.9. And so we reset it to 54. So this is a hot roll number 3, 95% reliability, no additional factors, and this is the G I told you is 10 to the 6. That's where this is defined. Okay, so enter this value 60 again, and you wait for a moment, and it's going to actually give you all this plus. Now the plot is correct. You can see that the values that I get are up here, okay? And this value is also correct, okay? So we have plotted these values, and what you can see is that your plot actually gives you the life cycle of what your N looks like. But I'm going to show you what this N, how it is calculated. But I wanted to show you again in this example, you have the conservative approach or you have the traditional approach. There is no need to put extra burden to your structure to have less life cycles when you can have more. So purpose of this example, we use a traditional approach. But know that this approach also exists, and you may, in many cases, it may be beneficial to use it. So I'm going to show you how I actually calculate this value. To calculate this value, you have 2 lines, one that goes from here to here, the other one that goes from here to here, okay? And those values are given by the following equation. For the case of low cycle fatigue, so that would be the first line. Uh, so here, this is this line that actually starts here at 70, okay, and goes all the way to, this is SUT and goes to F times SUT. It's the first line up here, okay? So what you really want to do is you want to find your SN plot is actually equal to A times N to the minus B. How you calculate this? You calculate this in the following manner. This is a log plot, so you can say your A is equal to S1 over N over B3, your B, but you need to find your B. So your B will equal to log base of 10, or you can use natural log, also gives you the same answer. S2 divided by S1 divided by log of N2 minus N1. Now here, so the coordinates here, if I use this as S2, S2 will be F times SUT, and 2 will be 10 to the 3, S1 will be SUT, N1 will be 10 to the 0, that will be actually equal to 1 cycle. So you replace these numbers in here, and you can show that the values that you get for that particular plot is 60 n to the minus 0.015. And then the second line, for the second line, you can also show that you go from here. Now that particular line to this line, your S2 will be SE, your N2 will be 10 to the 6, because this is the value. Remember, this is the plot I'm doing. This is your endurance limit. S1 will be F times SUT, and N1 will be 10 to the 3. You can use the same equations. And you can show that your Sn is equal to 183.826 n to the minus 0.77. Okay, so in your problem, if I really wanted to find the value, right, I know what my S equivalent is. So, and you saw from the plot, you're actually plotting right there, right? This was your S equivalent from your Goodman stress. So what you would do is you put your S equivalent and say 183.26 n to the minus 0.177, and then you can solve for n very easily, right? So just to show you how to do this once, you take this value that was 2949, this value, divided by 183.826, okay? And then you take this to the power of 0.177, that would give you n, okay? So you just multiply both sides by the opposite of this. So this is how you actually get this, sorry, this would be minus 1 over 0.177. Okay, be sloppy. So this is the value that you will actually get. Now, the problem was is asking, so from the plot, if you go back to the plot itself, we found that your n using the traditional approach gave me a value of 288. Okay, this is cycles, and your problem says that this is happening in 2 minutes. Every 2 minutes, in one cycle is repeated every 2 minutes. We know there are 60 minutes in 1 hour, and we know that it's working 8 hours per day. So let's see the life of the structure. It says the life of this particular structure is 301 days of life. So this structure roughly it has 300 days of life. So if you're going to give a warranty, that's the warranty you want to give. Or you want to start your inspection after 300 days. Okay, so this is the life, how many life is actually left in your structure. This completes example number 1.